Rolling contact fatigue, better known as RCF, is a group of defects that occur on or close to the surface of the rail due to the stresses placed on the steel used to form the rails. Unlike some rail defects, such as tachier vels or longitudinal vertical splitting, RCF defects are not inherent from the manufacturing process, but are caused by the passage of trains. But how? It all comes down to the area where the wheel contacts the rail. This area, known as the contact patch, is actually very small. It is often said to be about the size of a pound or euro coin. Given the weight of a train, especially a fully laden freight train, you can appreciate that there is a lot of weight on that patch of rail. This acts straight down as a vertical force. Within the rail, it produces stress in a number of different directions. They act straight down, longitudinally down the rail length, and laterally across the rail head. These stresses are shear in nature. This means it's trying to tear the rail steel, like you trying to tear a piece of paper. Each time a train wheel passes across the rail, the steel forms a little bit more. So, after a while, it eventually tears on a microscopic level, generating a crack. This is where the name rolling contact fatigue comes from. The rate at which this happens is dependent on a large number of factors that we'll cover later. These factors also determine what happens to the crack now and the defect that results. So what are these types of defects? Gauge corner cracking. As the name suggests, this defect appears on the inner corner of the rail where the wheels run, the gauge face. The cracks spread or propagate across the head and can be tightly packed together. As they grow, they can join up, leading to sections of the surface coming away from the rail. This is then made worse by further trains passing through the area. Running surface cracks. Similar to GCC in nature, however, this defect is located mostly on the crown of the rail. When these cracks join up, the material also comes loose. This is known as spooling. Shelling defect. Shelling defects are up next. These defects appear when cracks initiate 2 to 8 mm below the gauge corner and start out as dark spots on the rail, similar to squats. The cracks that cause shelling defects tend to extend deeper into the rail, known as a transverse crack. This means that when the material does come away, it's in larger chunks than the two previous defects we've looked at. These cracks can also continue to grow, and if not detected, can extend far enough into the rail to cause it to fail completely. Squats. Lastly, we have squats. Now, squats can and commonly do occur as a defect not associated with RCF, but they can be caused by an RCF crack, therefore they do need mentioning. The subsurface cracking causes a depression in the rail with a dark area, similar to that on a bruise on an apple. All these defects have their own characteristics, and sometimes it can be hard to classify which exact type of defect it is. The important thing to appreciate is that cracks, once created, can continue to grow within the rail, and importantly, below the surface. This means that, if not monitored effectively, the cracks could be growing down into the rail, leading to it weakening while it looks normal on the outside. This is fundamentally what occurred at Hatfield in 2000, where 4 people were killed when a rail, riddled with RCF defects, failed catastrophically under a passenger train, causing it to derail. So what are the factors that can affect the initiation and then propagation of RCF cracks? Well, they are wide-ranging is the answer, but we can split them into a few areas. First, we have factors that affect the wheel-rail interface. These include both the profiles of the rail and the wheel, the geometry of the track, such as its curvature or the level of cant, the characteristics of the train, track geometry faults in the area, and the gauge of the track, just to name a few. All these factors can subtly change how the wheel interfaces with the rail and that all-important contact patch. Now, we have the rail. As track engineers, we tend to focus on this, rather than the wheel, given that we can influence the rail more readily. The metallurgy of the rail plays a big factor, especially its resistance to shear forces. This can be affected by heat treating the steel, or varying the grade of steel used. This can often be a balancing act, as harder steels are less able to deform, so may fracture more easily when they do start to fail. It can also be an exercise in balancing cost versus benefit, as more specialised steels can be a lot more expensive. There is also then the ongoing management of the rail. Lubrication applicators can be fitted to the rail so that trains can pick up grease as they pass. This can reduce the shear forces and prevent RCF forming at such a fast rate. Rail grinding and milling, undertaken by specialist trains, can also be undertaken to remove the surface cracking and reprofile the railhead. This again increases the life of the existing rail. As with any defect, being able to detect then monitor its deterioration is key to managing the risk posed by it. The use of both train and hand-borne inspection equipment allows large areas of rail to be inspected and the sites of RCF identified. Specifically, a process known as eddy current is very effective for detecting these surface cracks. One of the challenges of RCF is that if re-railing is required, the amount of rail that needs replacing can be extensive. This is because welding rails with RCF can cause the cracks to increase in size when the heat is added. So unaffected areas or areas of light RCF need to be found so that the welds can be installed. So now you know about RCF, what causes it, the types of defects, and the factors that affect how quickly it appears. I hope you found this video interesting and useful. If you have any questions, do drop them in the comments below. And please do hit that like button and don't forget to subscribe.